What is the reward of a scientist? I think it's pretty simple. It's discovery. It's refinement of knowledge. It's the movement towards the ultimate answers. That is what every scientist works towards. That is, I guess you could say, their cake. We're in computer science. It's on the doors, it's on your syllabus, it's probably going to be printed on your degree. Having branched from the math and engineering departments at institutions such as MIT, surely computer programming is inherently scientific, right? This is Donald Knuth. He's considered one of the most legendary programmers of our time. He wrote a 3-volume collection of algorithms and software patterns that are the underpinnings of much of what we have in computer programming today. Even some of our most skilled coders have a hard time fully comprehending some of Knuth's algorithms. He's a brilliant mathematician. But he titled his collection, The Art of Computer Programming. In an article explaining why, he said, "We have seen that computer programming is an art because it applies accumulated knowledge to the world, because it requires skill and ingenuity, and especially because it produces objects of beauty." Computer science, as it refers to any branch of programming, I've discovered, is a total misnomer. Science is built on laws, which, while we don't fully comprehend them, they are unchanging. If I were to drop this phone, it's going to land on the floor. We have Newton's laws of physics that tell us that, and while those laws, our understanding of them is incomplete, they pretty much hold true. Anywhere on the planet that I go, if I drop this phone, it's going to land on the floor. There's no two ways about it. I'm going to have to use another law of physics to counteract that. The problem is, in programming, we don't actually have any laws we can fall back on. Now, we do have laws of computer programming. This is more the tongue-in-cheek variety that attempts to explain how this industry is very wibbly-wobbly, timey-wimey, as Doctor Who might say. Anytime we probe into any of these assumptions, any of these so-called laws, they fall apart, or they just cease to work entirely. Now, a lot of you are computer engineering majors, so you might be thinking right now, okay, hold on, Mr. McDonald, what about physics? We're using computers, we've got circuit boards, we've got resistors and transistors, and this whole thing is built on physics. That has got to factor in, right? Yes, it does, absolutely. In the same way that the science of color applies to painting. Proponents in schools of every style of painting exist, and while they lend volume and popularity to each style, they do little to disestablish the others. And science alone cannot explain these styles. So let's look at a few paintings. We have Washwoman on the Banks of the Durance by Paul Gauguin. This is realism, or fairly close to it. You almost feel like you could walk into the painting. You've got blues and greens and whites and tans. And then we move over to Claude Monet, and now we're starting to get into the Impressionist era. Now we're capturing glimpses of light and little fleeting aspects of the scene. We still have many similar colors, but we're not quite in realism anymore. Then we go all the way over to The Blue River by Auguste Renoir, and we are fully deep into the Impressionist era. Now we're capturing movement and light and feeling. And then we go over to At the Water's Edge by Paul Cézanne, and we have completely left realism behind. Cézanne is in the post-impressionist movement, about to touch off Cubism. And still many of the same colors. We got some blues, lots of greens, whites, browns, but it is completely different than Gauguin's realism. While the paints are very similar in composition, they're very similar in how the light reflects off of them, the science of color applies the same to each of them, they are very, very different works because they're different styles. Now, in the programming world, we have this funny term that we throw about called best practice. This suggests that there is a way that should always be followed and always works, no matter what. There is no such thing. We have good practice, which we should follow, we should understand, we should stick to it until we have a good reason to depart. But good practice varies from one language and one style and one goal to the next. And it is actually just a guideline. None of those painters were wrong in how they painted. The paint got on the canvas, they're good. They followed the styles and the practices of their particular school of painting. Let's talk about another place that has guidelines, which is music. Music is built on the same concepts of keys, rhythm, meter, harmony, and so forth. But we apply those same rules in very different ways. We have, by way of example, Beethoven. Here we go. Very beautiful piece of music. You can't dance to it unless maybe you're at one of those Jane Austen era country dances. Then we fast forward in time to the U.S. Army Blues. See if I can get this to play. Uh-oh. Get back your technology again. There we go. That's something we can dance to. Why? Style. They swing it. They have a very different way of playing music than Beethoven. We cannot tell the U.S. Army Blues to play it straight because that wouldn't be jazz. And in the same way, we can't tell Beethoven to swing it, first of all, because he's dead. Second of all, because he's not playing jazz. He's playing classical. Same rules, completely different applications. So we learn a lot of these really nice sounding rules and methods in computer programming that seem to work when we apply them to our homework problems. But it's like we're making tiny Lego models. And as long as we're making tiny Lego models, we don't really have to be aware of the fact that the table is rickety and it's about to fall apart. As soon as we start building anything larger on that table, things completely crash down. Alan Kay described this as, imagine you're building a doghouse. And the doghouse is, it turns out pretty well. You're pretty proud of it. So you think, all right, all we have to do is scale these blueprints up, and we can build a Gothic cathedral. He says when you blow something up by a factor of 100, it gets by a factor of 100 weaker in its ability. And in fact, what will happen to this doghouse, it would just collapse into a pile of rubble. The most popular response is to say, well, that is what we were trying to do all along, put more garbage on it, plaster it over with limestone, and say, yes, we were really trying to do pyramids, not Gothic cathedrals. Alan Kay, by the way, invented object-oriented programming and the language Smalltalk, which, while you may not be using that directly, you do use many of its concepts in modern programming languages. The truth is, we don't really fully understand how programming works. These machines seem to defy our understanding. Eric S. Raymond, in his book, The New Hacker's Dictionary, tries to describe a lot of the weirdness of the programming world by writing down the common slang that we had in the programming world. And this stuff exists. So, for example, we have Schrodenbugs. A Schrodenbug is a design or implementation bug in a program that doesn't manifest until someone reading the source or using the program in an unusual way notices it should have never worked, at which point the program promptly stops working for everybody until fixed. Though this sounds impossible, it happens. Some programs have harbored latent Schrodenbugs for years. Or we have Heisenbugs. A bug that disappears or alters its behavior when one attempts to probe or isolate it. I have seen at least 3 Heisenbugs in my career, and they are a pain to try and debug. So we have all these weird things grinning out from the darkness at us like Cheshire cats, and we begin to feel like we've fallen down the rabbit hole and we're in Wonderland. And indeed, if you spend any amount of time around programmers, you will discover that we are all indeed mad. That is not to say, however, that the world of programming is illogical by any means. Like Wonderland, it follows the rules of literalism. If you read the books, it's kind of funny. The Mad Hatter, the reason he's stuck at that tea party is because he said he was killing time, and you don't use metaphors in Wonderland. because it comes to pass literally. Father Time took umbrage with it and refused to work for him ever again. Computers act in much the same over-literal way. Ever done this? Spends 2 weeks fixing a huge bug in code that appears to be an unfixable problem, missing period. Has happened to me. In my case, it was 4 days and a missing semicolon, but it happens. Very often falls apart in very large programs. So how do we overcome this obstacle when we're trying to learn how to program? We study large programs. In Dreaming in Code by Scott Rosenberg, which is one book I believe every programmer with a pulse should read. It's a hilarious read at that. He quotes Richard Gabriel, a distinguished engineer at Sun Microsystems who was involved in Lisp and object-oriented programming. Richard Gabriel said, "My view is that we should train developers the way we train creative people, like poets and artists." People may say, well, that sounds really nuts, but what do people do when they're being trained, for example, to get a Master of Fine Arts in poetry? They study great works of poetry. Do we do that in our software engineering disciplines? No. You don't look at the great source code for great pieces of software, or look at the architecture of great pieces of software. You don't look at their design. You don't study the lives of the great software designers, so you don't study the literature of the thing you're trying to build. So if programming is not a science and we have no real laws to fall back on, what do we build on? Well, Gerald Weinberg says if builders built buildings the way programmers wrote programs, then the first woodpecker that came along would destroy civilization. This is often cited as Weinberg's second law. We have built everything in the programming world layer upon layer upon layer, one idea on top of another. We start down at the lowest level with the binary, obviously, our ones and our zeros, and even that is not law because the way the binary is interpreted depends entirely on the processor you're using, whether it's an ARM or an AMD or an Intel or a PowerPC or any number of processor. The way they interpret binary is very different. We've standardized things to make things easier, but there's no actual law, just our ideas. But we don't like working in binary. It's a little hard to work with, so we have assembly languages on top of that. And we're still ultimately just shuffling bits around, but it is a little closer to English. We have nice, handy commands like move and copy that make life easier. And then we move up to languages like C and Rust, low-level languages that are still closer to English, but still allow us to access the bare metal, the memory on the computer, and to move things around. But since C is still hard to work in, we build languages like Python and Java and C++. And we keep working our way up, building layer upon layer upon layer, which on the one hand allows us to build on top of other people's work, but on the other hand, when something falls apart in the middle of that stack, weird things begin to happen. Joel Spolsky said, abstractions fail. Sometimes a little, sometimes a lot. There's leakage. Things go wrong. It happens all over the place when you have abstractions. Spolsky is the founder and CEO of Stack Exchange, which is the company that runs Stack Overflow, and he is also a former Microsoft developer. This is often cited as the law of leaky abstractions, by the way, which is one of the articles I linked to on the resources page. Now, obviously something works. We have some things right, otherwise the machines we work on would not be functional at all. So we have to understand what currently exists in order to make it better. The trick is that we take nothing for granted. The only programming laws are the ones that we invented, so we need to ask the question, why do we do it this way? And then demand a better answer than, because we've always done it that way. Spolsky again said, although C is becoming increasingly rare, it is still the lingua franca of working programmers. You need to spend at least a semester getting close to the machine or you'll never be able to create efficient code in higher level languages. This is from an article called Advice for Computer Science College Students, which is an excellent read. If you read nothing else on the resource page, read that. I know C. I use it very, very rarely. It's kind of a painful language to work in. But I use the skills that I gained in learning C on almost a daily basis. It helped fine-tune my understanding of how the computer was doing things. And if you don't want to learn C, by the way, learn Rust, learn some other low-level language, although C is still at the heart of many of our technologies. So since programming is not a science, we need to approach it intentionally for what it is, an art. If we don't, things go very, very wrong. One of the main reasons most computer software is so abysmal is that it's not designed at all, but merely engineered. This is from Mitch Kapor's Software Design Manifesto. Perhaps most significantly, he founded Lotus Development Corporation, the makers of the first desktop spreadsheet software, 3-to-1 Lotus. Software engineering is as much a misnomer as computer science, because we can't build software like we build bridges. Every attempt to do so has ended quite badly. We have to instead design as artists. And that is never an accident. We have to approach that intentionally. Like any art form, you learn it through practice. And I'm going to eventually learn a lot about this campus's Wi-Fi. The need for design is why Legoland programming is inherently impossible. Legoland programming is this idea that somehow we will be able to make these little snap-together bricks, and we just click them together like Legos and we get working software. Many attempts have been made at this, and all of them have failed dramatically. Why is that? It's because, imagine trying to take the pieces of, say, LibreOffice, which is actually the software I'm using here, and breaking that down into blocks and rearranging it and getting a racing game. It's not going to happen. You have to tailor-make each piece for the purpose you need it for. So we need to be building software around what the user needs. We're designing software for people, not for computers. And I think it's very easy to lose sight of that. We need to decide what we want to accomplish, and then we figure out how to build it. Keep in mind that nearly all of the limits of programming are ones that are there because of decisions we've made before. Usually, the question is whether or not it is practical to work around the limitation, or is this going to involve us completely rebuilding how we interpret binary altogether. But we can decide if we can work around the limits, readjust our plan for the software, build it again around the user, and we go back and forth between adjusting or deciding if the limits are possible to work around and building for the user. But it always goes back to the user. And we need to talk pretty briefly here about Moore's Law, which states the number of transistors in a dense integrated circuit doubles approximately every 2 years. This is really cool because this means that we get more RAM, we get faster CPUs, we get better hardware about every 2 years. But we have yet to really reap the benefits of this because of Gates's law. The speed of software halves every 18 months. Why is that? It's because habitually programmers have their software filling all the available space there is. By way of example, this is one of my favorite comic strips online, commitsstrip.com. Young programmer talking to two experts says, in fact, an infinite loop in our own JavaScript code was sending so many AJAX requests that we almost DDoS'd ourselves. But it was easy to fix, today with the cloud. What does this have to do with the cloud? Simple. You just have to launch as many instances as you need to hold the load. So in case he didn't catch that, instead of fixing the infinite loop in his code, he simply expands the space that the software has to work in, thereby hiding the effects, but not fixing the problem. This may seem like a cartoon. By the way, this is a true story, I found out. But here's a couple other examples. Why should Windows 98 be faster than Windows 8? I work on Windows computers. If you want to try this out, install both on their ideal specifications for that operating system, run it for 3 months, and then see which one will let you hit the power button and actually start up a program first. It's a little scary. Why should newer software be heavier? We had video editing software that ran on 64 megabytes of RAM. Now our video editing software, which doesn't do that much that's new, requires sometimes, 16 gigabytes of RAM in minimum specifications? Why? It's because at some point programmers stopped thinking about conserving resources. They figured, I have all the space, I've got 8 gigabytes of RAM, I could never use it all, I'm good. And they stopped thinking about optimizing their programs. Here's one quick reason why optimization matters. If you waste 75% of the resources available to the code on not optimizing, that is 75% of the resources you are not using to do something innovative, useful, cool, exciting. It's just wasted space. Also want to touch on fads for a moment. There is no cloud, just other people's computers. The cloud is the same web service we've been using for the past 20 years. We just stuck a shiny new marketing label on it. Now, don't get me wrong, Docker's a really cool idea, okay? We've got some new software out there, some really neat things. But you shouldn't be using anything on the merit of it being trendy. I have seen so many programmers say, oh, I'll just solve the problem by moving it to the cloud, as if that's going to immediately fix their problem. You should make every decision in designing your software based around what's going to best fulfill my project's needs, not whether or not it's trendy. My company is just as quick to use new technology like cloud software as we are to use old technology. Like there's actually a problem we were able to solve quite effectively, most effectively with macros. But it worked because it's a tool and we knew where to use it. Finally, if programming is an art and not a science, we need less foremen to manage an engineering project, and we need more curators to manage what it is, an art project. So what is a curator? A curator is someone who maintains a collection, such as of art. They expand the collection, and they present the collection to the public and other professionals. Now, substitute the word code in for collection. Maintain code, expand the code, present the code to the public and other professionals. This is the job description of every programmer on the planet. Projects don't succeed by accident. Communication is central to everything you're going to do as a programmer. And project curation is not the responsibility of just the team lead or just the project manager or just the lead developer, but it's the responsibility of every single person. You guys have a gorgeous art gallery over here in the Light building. It's beautiful. I saw it the other day. But imagine if there was only one person who helped maintain that room and everyone else just dumped the artwork on the floor. One of two things is going to happen. Either that art gallery is going to look absolutely terrible, or you're going to overwhelm the one person that's running it. I've just described a large majority of software projects today. We have to take project curation as our personal responsibility as coders. Joel Spolsky said the difference between a tolerable programmer and a great programmer is not how many programming languages they know, and it's not whether they prefer Python or Java. It's whether they can communicate their ideas. Communication really is key. So how do you curate a project? I believe every project, open or closed source, needs to be able to answer 7 questions. 6 of them are rather familiar. Who, what, where, when, why, how, and I like to add what next. The README file needs to be present in any project, whether it's big, small, open source, closed source. This could be a text file, it might be a markup file, it might be a collection of files, but it answers the same questions. Who created the project and who is in charge of it if there's bugs, if there's feature requests, if there's contributions. What does the project do, in short? Where is the canonical source? If it's open source, where can we download the latest version of the code? If it's closed source, where's the binary? Where's the official version? And when were changes made? Your users are only going to know about changes in your program through the change log. Second, we have documentation. Documentation describes what the project does exhaustively. Now, documentation does not have to be boring. Imagine you have someone, your ideal user. Think of your ideal user. They're sitting in a chair in front of a computer with your software on it. They turn to you and say, I have all the time in the world. Tell me absolutely everything your project can do. Man, you'd be excited. You'd be showing them all sorts of cool stuff. You'd be showing it off. That's what documentation needs to be. Get us excited. Show us everything you built into this. You built something cool. Show us all about it, and then tell us how we, as the user, can use it. Users are pretty unforgiving individuals. They will give you usually about 5 minutes of their time, in which time they expect to have something on your code working. If nothing happens in the first 5 minutes, they're closing the program, walking away, and probably never coming back. So you need to document how to get started doing something meaningful. And the documentation is where they're going to look for that information. Now, you may be thinking, okay, I got this covered. I've got Doxygen hooked up, I've got Java Docs. I'm good. I just hit the button and it builds the documentation. No. Autodocs, also known as API documentation, are not the same thing. Most API documentation is like teaching someone how to use a toaster by explaining the electrical specifications of the heating element. We don't care that the render function takes a string, 2 integers, and returns a Boolean. It doesn't matter to the user. The only person it matters to is to the internal developer. We, the user, want to know how to make the code do something. You have to write that by hand. Sphinx is fantastic for that, by the way. It lets you write it in restructured text. It'll export to PDF. It'll export to really snazzy HTML pages. It goes to LaTeX. It goes to Mandocs. Any help format you can imagine. It's a free technology. You can download that. We use it at Mousepot Games. It is fantastic for writing docs. Now, don't get me wrong. API documentation, again, does have its place. If you're writing a library or a code and you want outside contributors, it's very helpful if you're maintaining the code, but it's not the same thing as documentation. All right, next we have comments. Ew! Comments. Most people don't write comments. How do I know this? I interview people. Most people don't write comments. Comments need to describe why we wrote the code the way we did. It does not describe what the code does. Reading through the code, I can tell it's a for loop going through a vector of people, objects, and comparing the last name. That's really easy to tell. I just don't know why it's there. So don't reiterate what the code does, describe why you put it there. Oh, I was searching for the last name of the user in the address book. Oh, well, I can tell you how to optimize that. Then all you have to do is stick that into a map, use the last name as a key, and use a binary search. Now we just optimized the code. We couldn't have known that information without the comment describing why. We have what I hope isn't, but apparently is the first commenting standard in the industry. At Mousepot Games, it's called the CSI standard. This describes how to write great intent-focused comments, how to make the comments not completely dry, so it makes reading the code a little bit easier. You can get that at standards.mousepotgames.com. I have the link on the resources page. One more. What's next? Every project needs to track tasks, bugs, features, goals. I don't care how big or small the project is, or if there's one person or 1,000 people working on it, you need to track tasks. There's tons of tools for it. Use GitHub, use Fabricator, BugTrack, Mantis, Redmine. If it's just you and you're desperate, pull up a spreadsheet, but for the love of all things digital, please track your tasks. This enables you to prioritize things. No matter how much you think you can, you will not be able to keep all of this in your head. It lets you track progress, so you know what's done, what needs to be done, and it's vital to communicating with other programmers. We have a rule at our company. The rule of task states, if the goal won't be finished in the next 10 minutes, make a task. Most task trackers, it takes you about a minute at tops to create your typical task or bug report. So it doesn't actually eat up that much time, and it saves you a lot of time in the long run. We have another standard at our company called Quantified Task Management that makes this a lot easier. It is 4 measures that are measured on a scale of 0 to 5. We have priority, which is how soon, and gravity, which is how important. Those are not the same thing. You could have something that must be finished for the project to be done. We need to do 7 other things first. High gravity, low priority. Or you could have something that it'll take you 15 minutes, you're in that part of the code, it'll make it a little bit nicer. It's not super important, but hey, might as well do it while you're there, right? High priority, low gravity. We have friction, which means how much precedence is there. Because measuring difficulty is hard. It depends from one coder to the next, what technologies they're familiar with. But we can measure whether it's been done before. Are there tutorials? Is there code? Is there other things that we can work off of? Writing a hello world is F0. That is so easy. There's a million tutorials for it. Writing a program that's going to render fireworks on the screen, pixel by pixel in Rust, is an F5. You're on your own. There's nothing out there to help you. Relativity is the last measure. This is the probability of the task turning into what's called a black hole. These things exist. I've seen many of them. A black hole is something that takes up inordinate amounts of time. You put in an hour, 2 hours, 4 hours, 8 hours, 16 hours, 2 weeks, 2 months, and you're no closer to finishing it than you were when you started. So relativity lets you say, I think this is going to turn into 1, or no, I don't think it's going to. Really helpful because you don't want to take on an R4 if you've got 10 minutes until class. R5, we reserve that for meaning this is impossible. It's going to require more time than there is in the known universe. At that point, if you encounter one of those, refactor what you're doing. It is actually impossible to complete an R5 task if it's turned into a black hole. I worked on a project where they had been using a terrible web platform to build an e-commerce website for 4 years, and we're no closer at the end of the 4 years than they were at the start of the 4 years. That is a complete black hole. No project ever pulls out of it. They had to throw away, they had to scrap what they were doing and completely rethink their approach in order to get that stuff. You can find this also at standards.massapodgames.com. That's also on the resource page. Keep in mind, Galora's 7th law: projects that get behind stay behind. You don't gain forward motion. Once you're behind, it just kind of stays there. So to summarize, today we've talked about how programming is an art. It's not defined by laws. So you have to understand what art has already been made. So you can design your own code, not engineer it. And so you can curate your project effectively, curating your work of art. The idea of computer science is a very alluring one. It states that we can somehow finish. That someday all that's left will be to sweep the floors, polish the trophies, and call it done. We have finished computer science. But this is inherently impossible. This is the cake that so many have toiled for, but it cannot exist. Because just as we will never paint every painting, and we will never compose every piece of music, we will never write every program. There's always one more idea, one more optimization, one more improvement, or as the law of cybernetic etymology so aptly puts it, there is always one more bug. So what are we doing this for? What is the goal of a computer programmer? I believe it's found in the art. I do this because no matter how long I'm programming, I can always learn more, I can always build more, I can always find a new idea, a new avenue, something that no one else has ever done before. There is always going to be possibility, no matter how long I've been writing programs. That's what I work for. I'm an artist. That's why I program. So are there any questions I can answer? I really like questions, so feel free to, yeah.
Out of how many games you've built, how many are just on Symposium, like using?
Well, at the moment we have developed 2 open source games that are available on our website because the main one that we're putting all this time into is not going to be done yet. I would like to say that both of them are. One is indirectly because it works in the command line, and that was actually designed for my friend with cerebral palsy so that she could play with the keyboard. And so people who use the command line, they can adjust the colors to whatever is easiest for them. The other game we have is called Infiltrator. It's a party game, but I designed it so that the background color is not white and the foreground color is not black. That's like the worst possible combination for someone who's dyslexic. I designed it so that it's easy on the eyes, it's still visible, but it's not likely to set off the symptoms of dyslexia for a lot of people, including myself.
Do you offer the font as well?
We do. We actually have a font that we use called Open Dyslexic. It's an excellent, it's a free font online. You can download it, you can use it however you like. It is designed specifically to help prevent letters from flipping over or moving because the bottom is weighted. It's really cool how it's designed. But that doesn't work for everyone, so in the finished game we're going to be aiming for offering many different kinds of fonts. In Infiltrator, which is the only game I built that has an interface so far, we use a sans serif font, so even though it's not open dyslexic, it's still easier to read. It's not likely to change as much as a serif would.
I'm dyslexic, that's why I asked.
Awesome. So we have the same superpower.
Yeah.
Learning it.
There's another font called Dyslexia that is really good also. And it's free.
Excellent. There's actually a talk I listened to that, this is not on the resources page, unfortunately, but if you look it up, it's called Death to Icon Fonts by Sarah Davies. And she is a UI designer who is dyslexic, and she talks about how to design user interfaces, specifically web user interfaces, for users who have dyslexia. So that is an excellent talk. S-E-R-E-N Davies. I see wheels turning slowly.
What made you decide to do your own company, ultimately? You mentioned it briefly, but could you talk a little bit more about what made you decide?
Sure. Yeah, the reason I wanted to start my own company was because a lot of education, the standard in the educational software industry was a little bit alarming. First of all, most companies had disregarded the field as having any economic merit whatsoever. And so most companies wouldn't get behind educational software. They just figured it was a waste of resources. Second of all, because the educational software companies that did exist charged huge amounts of money to schools, sometimes $2,000 to $4,000 a year to be able to use the software. And I didn't want to charge that much. So we are trying to set the company up in such a way that we're charging as little as possible to keep the lights on, to be able to pay people, but to be able to deliver this to as many schools as possible. And I believe the best way to do that was to found Mousepile Games. Really quick, I realized something I kind of glazed over when I was talking about commenting. I think the biggest argument for commenting your code is that you will not be able to figure out your intentions 6 months after you've written the code. You won't be able to figure out your intentions 6 weeks after you've written the code. And I know this because I get into code I wrote 3 days prior, and I'm like, why was I writing it this way? So taking the extra time to put in those comments actually saves you far more time than what you wind up spending on it. Yeah.
What are the biggest optimizations that you need to do to use an older machine for new software?
I believe a lot of it comes down to, it's really tricky because it depends on what you're building, and I have to constantly fight the urge to go into what's called performance bean counting, where I'm over-optimizing things that don't matter, because it's so easy to get into that. But I think one of the biggest things, actually probably the largest, is watch your dynamic allocation. I have an article which I linked to on the resources page called Don't Annoy the Warehouse Guy. To kind of summarize the analogy I used in that, imagine if the RAM is a warehouse, and there is one guy that runs it, and if you need something out of that warehouse, or you need something stored in that warehouse, he has to drive his forklift around and move things around, find a spot for it, put it in, and bring it to you, if you need it brought to you. And ordinarily this works out pretty well because you have the cache, you've got your little office where stuff is brought and you can just work with it. But the problem with a lot of dynamic allocation, especially many data structures, is that you will start out by allocating, you'll say to the warehouse guy, I need space for 4 pallets, or say in a string 4 characters. And so he'll make space for that, and then he comes back to you and you say, oh, actually I need space for 5 of them now. Okay, he goes back, now 6, now 7, 8, 10, 12, oh, forget that, you only need 10. Nope, I'm going up to 12, 14, 20, 100. And by that point, he's regretting his career choice. That is where we lose, I think, a lot of performance. A lot of that gets sucked up. The reason our data structures, I believe, are as fast as they are is because instead of just dynamically allocating one thing at a time, we do what I call over-allocating. And that is, we allocate something in a chunk. We start with, like, say, 8. We run out of space, and we go to 16. And then we go to 32. And we're experimenting with some different patterns for that. But if you watch when you allocate, only do it when you need to, and then try and leave yourself a little bit of breathing room so you don't have to ask the CPU to go back and allocate all over again. So, and on that note, know your abstractions. If you're using a library, especially like in Java or in Python, you should understand how things are working under the hood well enough to know if there's dynamic allocation occurring. So you can use that to make decisions. There have been a few times where I've discovered I didn't need a vector, I just needed a static array because I wasn't going to change the sizes, and I was able to save dynamic allocation there. Yes?
Outside of bad programming practices, what do you think are the main reasons why programs now use up so much space and memory?
Well, I actually have to say that, yeah, I think the main reason actually is bad programming practice. I have to qualify that by saying it compounds one on top of another. So, which is one of the reasons I avoid Java, is because Java has a lot of these bad design decisions in certain aspects of their library, their standard library, and so we use it without realizing it. But that aside, I think the other thing that causes software to take up more space than it used to is because we have fancier graphics, we've got fancier features, and I don't think that's so much of a problem, because if we're doing something actually new and innovative, then it's worth using the space that Moore's Law has given us. I think the only problem is when we are, again, wasting the space instead of using it for something cool. Now that said, I think the other problem can be if we're trying to make something look flashy or exciting just because we can, as opposed to it needing to. I'm very unusual in my web design. I only use HTML and CSS, very little JavaScript. I hate websites that fly and flash around and things slide all over the place and it takes over your scroll bar and everything. And I think a lot of the times when we're designing stuff, we're trying to make it look cool, we're trying to make it look trendy, and so we wind up using extra resources on these effects that we don't ultimately need. So I think the other part of it is prioritizing, does this toolbar really need to slide onto the screen and have fireworks coming off of it? Or can we just have it sitting there? I think that's probably the other place where we lose optimization. And again, it's about designing for your user, knowing who your user is. Yeah?
I had a question about just the business side of it. If all of your code is going into an open source repository, how is the charging schools working if the code's open available for anybody to take?
Right, that is an excellent question. I'm glad you brought that up. I'm going to give you the short answer, but for the long answer, read The Cathedral and the Bazaar by Eric S. Raymond. This was the book that started the open source movement. He talks about how this can be economically viable, how to have open source projects and still keep the doors open. But basically what we do is that we follow the philosophy of free the code and sell the content. So instead of locking down the code and saying, this is our proprietary, this is our money maker, this is our cash cow, we're saying, you know what, the code is something we're okay sharing, and instead we're going to lock only enough to keep the content safe. Operation Inspire itself is not going to be open source just because we don't want to expose how we are keeping the content secure, but the entire game engine is open source. That's how we manage that. Briefly, the three models that you can follow to have an economically viable open source project. One is, like I mentioned, free the code, sell the content. The second is free the code, sell the support. If this especially works for business software, it's like you can use the code for free. If you want technical support for it, if you want us to help you set it up, then we can do that as well. And I think the third one, Eric S. Raymond describes, escapes me for the moment, but I think the third one is,
it's where you free the code and sell the hardware. He talks about how if you're building hardware, don't close source the driver, because your competitor's probably going to be trying to copy it anyway, and they're just, by imitation, they're just wasting time anyhow. So that isn't even a factor. If you free the driver, if you free the code that runs the hardware, and you sell the hardware, you're still the only person that sells that hardware, but the software is free. So those are the 3 ways I think you can make an open source project economically viable. Does that answer?
Thank you.
Good.
All right, let's take them.
Cool.
For links to many of the articles and books mentioned in this presentation, visit indelibleBluepen.com/resources/cake.